All right, so in this video, we're ready to talk about permutations and combinations. I want to start just with a basic problem. The idea is that we have some set of 10 books, and I have only room for 3 of those books on a bookshelf. And I want to know how many ways can we arrange those 3 books on a shelf. And so I'm going to think about this as having 3 spots. And how many choices do we have for the first book? We have 10 choices. And how many choices do we have for the second book? We have 9 choices. And how many for the third book? We have 8 choices. So altogether, this is 10 times 9 times 8, or there's 720 different ways to do this. And there's another way that you can represent this quantity. You can think about this as 10 factorial over 7 factorial, where what I mean by factorial, so 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And 7 factorial is the same thing, just from 7 down. So a little iPad cheating here, but just from 7 downward. Okay, so those are factorials. By convention, 0 factorial is defined to be 1. 0 factorial doesn't mean anything necessarily by itself, but just so that everything works out nicely, we want 0 factorial to be 1. All right. So you can think of this as 10 factorial over 7 factorial. I think that that's a slightly more natural way to think about this rather than doing this process every time. In general, if I have a set with n elements, just say I have the numbers 1 through n, where n is some, whatever, it's 100, it's a million, it's 5, I don't care. How many permutations of that set are there? By a permutation, what I mean is a number of ways of arranging those elements. So maybe I leave them in order, 1 through n. That's one way to arrange them. Maybe they're in reverse order, n minus 1, all the way down to 1. Maybe they're randomly scattered. It doesn't matter. So I want to know how many ways are there to order that set of n objects. And so I want to also think about this as a multiplication problem or a product rule problem. We have n choices for the first element. We have n minus 1 choices for the second element. We have n minus 2 choices for the third element, and so on, until we're just down to having 2 choices and then finally 1 choice for the last element. So it turns out that the number of permutations on a set of n elements is going to be n factorial, which is exactly n times n minus 1 times n minus 2 and so on. Now, that's a permutation. Given that set of n objects, you can think about the numbers 1 through n. An R permutation is where you take R of those objects and then you just arrange those R objects. So for example, we had 10 books and we wanted to count the number of ways to arrange 3 of them. That would be a 3 permutation on a set with 10 objects. Okay, so we're going to denote that P of n R. So in other words, this 720 is P of 10, 3. And what I want to do is I want to come up with a formula for the number of R permutations on that set. And so we're going to have R spots. Okay, so there's R spots available here. We have n choices for the first item, n minus 1 choices for the second item, n minus 2 choices for the third item, and so on, all the way down to n minus r plus 1 choices for the last item. And so this is going to be n times n minus 1 times n minus 2, all the way down to n minus r plus 1. And you could think of this, it turns out, as n factorial divided by n minus r factorial, which is where we got the 10 factorial over 7 factorial from before when our r was 3. Okay, so this is the number of ways that you can have an R permutation. Now, this is different than what's called an R combination. With a permutation, the order matters. So it doesn't matter which set of objects you have, you care about the order that they're in. For a combination, it's the opposite. You don't care about the order, you care about what's the set of objects that you have, and you forget about the order. So this is going to be a number of unordered selections of R elements from a set with n elements. And so one example I like to think about is that if you were to think about the number of words, so the number of, I don't care if they're actually words, but just arrangements of letters, say of 2 letters from the using the letters A, B, and C, there's 6 words you can make. You can make AB, AC, BC, BA, and then CA, CB. So those are the 6 words that you could make using just 3 letters. And again, by words, I just mean arrangements of those letters. I don't care if they're actually English words or in a dictionary or whatever, I don't care. In contrast, let's say we have Adam, Bonnie, and Carol, and we want to make 2-person teams. How many 2-person teams can we make? And it turns out there's 3 2-person teams. We can make Adam and Bonnie, Adam and Carol, or Bonnie and Carol. There's 3 2-person teams we can make. The reason why this count is different is that we don't care about the order that the 2 team members are chosen. We just want to find a team. We just care about what's the actual objects that are selected. In this case, what are the actual people that are selected to join the team? And we don't care about the order that they're chosen. When you don't care about the order and you just want to count the number of ways that something can happen while ignoring the order, that's a combination problem. Okay, so that's a combination problem. And the number of ways, so the number of R combinations on a set of n objects is set n choose R. And it's written typically like this. So if you're ever in a math context, it's written like this. In some other contexts, it's written like that, C of nr. So n choose R. By the way, I forgot to say, before P of nr is said n permute R. Okay, just if you want to know how to say that. So to come up with a formula in general, it turns out what we're going to do is n choose R is going to be, let's first count the number of R permutations. So that's n permute R. And then for each of those choices, we're going to divide by the number of ways of ordering our set with R objects, and that's going to be R factorial. So in other words, this is going to be n factorial over n minus R factorial times R factorial. And I don't want to get too much into the, I don't want to be too nitpicky with the math derivation here. That's the formula for n choose R, or if you want to write it, C of nr. And that's the number of ways to choose R objects from a set of n objects. So you can think about that as much as you would like to, but I just want to move on and calculate with it. So the first thing that we'll do is we'll compute by hand the following. These, by the way, are called binomial coefficients. There's something called the binomial theorem, which involves these. There's a lot you could say about these binomial coefficients. They're actually the values from Pascal's triangle. So Pascal's triangle is the thing that you studied in algebra or wherever, where you do ones all the way down, and then to get the next value, you add the 2 previous values. So 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4, and so on. So 1, 5, 10, 10, 5, 1, and so on. And it's symmetric from left to right and right to left. So what I want to do is let's compute 3 choose 2. Let me actually do one more row. 1, 6, 15, 20, 15, 6, 1. So just one more row of Pascal's triangle. And now let's just actually compute 3 choose 2 and 6 choose 3 and a few of these others by hand. And so the idea is that we have 3 objects and we want to choose any 2 of them. We want to think about how many ways are there to do that. Well, 3 choose 2 is going to be 3 factorial over 2 factorial divided by 1 factorial. And just to be consistent with myself, I put the 1 factorial first. Of course, the order that you multiply integers isn't going to matter. We're going to get the same thing. And 3 factorial is 3 times 2 times 1. So that's 3 times 2 times 1. 1 factorial is just 1. 2 factorial is 2 times 1. And altogether, this is going to be 6 over 2, which will give you 3 is your answer. So 3 choose 2 is 3. And that's consistent with what we found. If we have 3 people and we want to choose teams of 2 people, there's 3 ways to do that. If we have 6 people and we want to figure out how many 3-person teams are possible, it's a little harder to count by hand now. So 6 choose 3, what we're going to do is we're going to take 6 factorial divided by 6 minus 3 factorial, so it's 3 factorial, divided by 3 factorial. And so we can just calculate, this is 6 times 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1, and again 3 times 2 times 1. And then let's just simplify everything that we can, and this simplifies very nicely. The 3 times 2 times 1 cancel, and then 3 times 2 times 1 is 6. So that also cancels, and we're left with 20. So it turns out 6 choose 3 is 20. And notice that that's a value on Pascal's triangle. You always have to start counting with Pascal's triangle starting with 0. So you want to go to the 6th row, and so you're going to count 0, 1, 2, 3, 4, 5, 6. So that's the 6th row, and of course that's the one that has a 6 in it. And then you're going to count the 3rd object, so 0, 1, 2, 3. And indeed, you really do get 20. So these binomial coefficients are exactly the things that come up in Pascal's triangle. By the way, 3 choose 2 was 0, 1, 2, 3. And then you want to count 2 items over. So 0, 1, 2. So this 3 right here is why that was a 3 there. All right. Next up is n choose 2. I'm sorry, 10 choose 2. And that's going to be 10 factorial over 8 factorial times 2 factorial. And that's going to be 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Should have made the number smaller. What am I doing? Divided by 8 factorial, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then 2 factorial is 2 times 1. I do not encourage you to write these out every time. I'm just writing it out to make a point here. Now I want to think about what's 10 factorial over 8 factorial. Well, notice that this 8 times 7 times 6 all the way down to 1 is in the top and bottom. So 10 factorial over 8 factorial is really just 10 times 9. Okay, that's really all it is. And that's 90. So this is 90 over 2, or 45. So it turns out that 10 choose 2 is 45. If you have 10 people to choose from, the number of 2-person teams that you can make is 45. You can make 45 2-person teams. On the other hand, how many 8-person teams can you make? Let's do this again. This is 10 factorial over 2 factorial times 8 factorial. And notice that our denominator is the same as it was before. It's just that the order of the 2 factorial and 8 factorial are switched. So it's going to turn out to be the same. But let's do it this way. 10 factorial over 8 factorial is 10 times 9. And then the 8 times 7 times 6 times 5 all the way down to 1 cancels with each other. Divided by 2 factorial, which is 2. So again, we'll get 45. And so I want to know, why are these two equal? So why are those equal? So think about that for a second. We can talk about that. Later. Okay, but think about why those should be equal. And here's a hint. If you make a 2-person team to go on a mission, that's the same as making an 8-person team to not go on a mission. Okay, so that's more or less the answer there. So we're not counting the teams themselves, we're counting the number of ways to make the teams. So for every 2-person team you make, there's also an 8-person team. There's 8 people that's not on the team. So there's kind of a 1-to-1 correspondence there. So spoiler alert, I just ruined it. Next up, let's say we have a standard deck of cards. How many 7-card hands are possible? You don't care about the order of cards that are selected when you have a 7-card hand. You just care about what are the actual set of 7 cards. So it turns out to be 52 choose 7. Okay, which I'm not going to compute what that is. You can do that. All right, and then finally, let's look at, or almost finally, let's look at number 10. So we have a standard deck of cards. We're going to get a 5-card hand, and we want to find the number of 5-card hands that contain the 9 of hearts. And this is a little bit tricky. One way to think about this is take the deck of cards that you have and pull out the 9 of hearts. and you started with 52 cards. If you take out the 9 of hearts, you're left with 51 cards, of which you want 4 of them. So the number of 5-card hands that contain the 9 of hearts is 51 choose 4. I want to also put in 1 choose 1 in front of this. And of course, if you have one object, the number of ways to choose it is 1. There's only one way. You just choose it. There's nothing to do. There's nothing to show. Of course, the formula works, but the reason why I want to think about that, the reason why I want to put that in front is that I want to think about this 1 as how many 9 of hearts is there? Turns out 1, and you want to choose one of them. And then there's 51 not 9 of hearts. There's 51 other cards, of which you want to choose 4. Okay, I think that way of counting will be helpful for us. So now let's use that methodology. Let's use that analysis and count how many 5-card hands contain exactly 1 heart. So how many hearts are there? Well, there's 13, and we want to choose one of them. How many non-hearts are there? Well, 39, because that's 52 minus 13. You want to choose 4 of those. Okay, so there's 13 choose 1 times 39 choose 4 ways to get a 5-card hand with exactly 1 heart. On the other hand, what if we want to count the number of 5-card hands that contain at least 1 heart? And there's a few different ways to do this. You could count the number of ways that have exactly 1 heart, plus the number of ways that have exactly 2 hearts, plus the number of ways that have exactly 3 hearts. So that's 3 hearts and 2 non-hearts, plus 4 hearts and 1 non-heart, plus 5 hearts and 0 non-hearts. That's one way that you can do it, and that's kind of the long way. The other way you can do it is you can think about how many total 5-card hands are possible. And that's 52 choose 5. And then what you want to do is you want to subtract how many ways, what does it mean to have at least 1 heart? What's the complement of having at least 1 heart? Well, the complement or the opposite of that is having exactly none. So how many ways are there to get exactly no hearts? Of the 13 hearts, you want none of them. Of the 39 non-hearts, you want 5. And it turns out each of these will give you the same quantity. Okay. 2 more card examples here. How many ways are there to get exactly 2 hearts and 2 diamonds? So of the 13 hearts, you want 2 of them. Of the 13 diamonds, you want to choose 2 of them. Of the non-hearts and diamonds, there's 26 cards that are neither hearts nor diamonds, and you want to choose 1 of them. Okay, so again, I don't care what the actual number is, but that's how you count. And then finally, contain all cards of the same suit. There's 2 ways that you can do this. You can count how many cards are all hearts, plus how many cards are all diamonds, plus how many cards are all clubs, plus how many cards are all spades. These 13 choose 5 terms that I've just written down, you could have also written times 39 choose 0, but 39 choose 0 is just 1, multiplying by 1 doesn't change anything. So that's one way that you could do it. Another way that you can do it, and I think that this is instructive, is think about a particular case. Say, how many ways are there to get all clubs? And of course, we know that that's 13 choose 5 ways to do that. And then you want to think about how many ways are there to determine suits? Well, there's 4 suits. So 4 times 13 choose 5 is another way to do that. A slightly shorter way. Of course, these 2, it's easy to see that these 2 things are equal. Okay, but just 2 different ways to count there. As our final example, I want to think about, we have a hockey team of 20 players with 1 captain and 3 alternate captains, and we want to know the number of ways that we can get a captain and 3 alternates. And so what we're going to do is we're going to think about, we have 20 players. How many ways are there to choose a captain? Well, there's, of the 20 players, we want to choose 1 captain. Good. And then how many ways are there to choose 3 alternate captains? Well, how many choices are there for alternate captains? It turns out there's 19 because we can't use the captain. That's kind of a hidden assumption here, is that a person can't be a captain and an alternate captain at the same time. So there's 19 players that we could choose to be an alternate captain, and we want to choose 3 of them. So 20 times 19, choose 3. This is an example that for the first time combined our use of combinations and the product rule for counting. Okay, so this is our intro to counting in combinatorics. And again, we use this all the time when we think about probabilities, because the probability of E is the number of ways that E can happen divided by the total number of possibilities. So if we know how to count the numerator and denominator separately, then we can talk about probabilities.